Okay, all right. So how about before the lights go off, if they're going to go off? So, so I apologize, but I gave a lot of this talk at AWRA about a month ago, so it'll be a little bit redundant for some of you. But this was my prop for that talk, and this is the fluid that came out of the head of a Bakken well in the middle of the Williston Basin, just south of Williston. So this is the real deal. This is an example of the fluid that's coming out, and I'll talk a little bit more about this, or a lot more about this, with respect to the saline water that's also coming up with that oil. So for every barrel of oil you hear, there could be 1 to 3 barrels of this saline water that's coming up. Okay, so that puts it in perspective. It kind of sets the stage. And this is propent, the sand that they use for the hydraulic fracturing, either ceramic or silica sand. Just some examples of really what they use out there. So. Okay, and I'm honored to be here. It's the first time I've been in this building, and I'm impressed. So thanks for having me. All right. So we're going to talk about the water quality, really what the issues, but also what we've done so far out there in the Williston Basin, okay, in areas of energy development. And this isn't my work alone by far. It's a collaboration of several folks from different water science centers, USGS water science centers. Just recently working with the Energy Resources Program, folks out of Reston that have been working with the Marcellus Shale and other parts of the United States that are basically educating us and helping us go into this new arena with respect to sampling these produced waters. Working with folks from the safety program, working with folks from the Bureau of Mines and Geology when it came to the Williston Basin sampling, helping us determine which formations we're in, John Wrighton in particular. So, and also with these studies, just as a lot of you folks that look around the room, we have to deal with the public. We're working with well owners that are giving us permission to sample their wells. And also industry. When I first started in this, thinking that we're going to go to a oil and gas producer and ask them if we can sample their well to see what's in their water, I thought there'd be no way they'd let us do it. We have no enforcement, we have no regulation, and surprisingly, the open arms. We had a lot of help with respect to helping us understand what we're sampling, getting us set up, and folks spending the whole day with us in the field. So in reality, industry has been very welcoming to our projects. So. Okay, so for the presentation, just going to talk about conventional and unconventional oil and gas development, just the basics. Some water quality concerns in areas of energy development. Water quality study objectives, why do we care? Overview of the Williston Basin, the study area, description. We'll talk about the produced water sampling that we've done in 2012 and 2014, mainly in the Williston Basin. In 2013, we completed a pretty much baseline study of the Fort Union Formation, the Aquifer, groundwater study. We did that in 2013, and then other work in energy development areas, including the Bureau of Mines and Geology, DNRC, DEQ, other folks are working out there, and some proposed work that we'd like to see in the future. Sampling a domestic well in the Williston Basin and sampling a production well in the Williston Basin. Okay. So conventional oil and gas development, which has been around for well over 100 years, but in the 50s mainly in the Williston Basin was really the start of it. It was basically a vertical well with production underneath a seal, a trap, and you're producing the gas and oil with that trapped material in a more productive setting with respect to the permeability of the sandstone. With regards to oil and gas and unconventional oil and gas development, we're looking at, in the Williston, we're looking at wells that are maybe 2 miles deep vertically and up to 2 miles or so horizontal in direction. So quite a different setting. In a little more detail with the hydraulic fracturing and the unconventional oil and gas development that we see out there. Industry is very confident that the safeguards they have in place are very protective. Ideally, you're going through what we are considering our produced or our water resource, our groundwater resource, which is the bedrock aquifers, the glacial aquifers at shallower depths. But they're going down up to 2 miles deep and then 2 miles laterally, inserting a casing, cement lined, perforating this along the long laterals at different stages to increase the permeability of the surrounding shale, which we know they knew there was oil there for years, but to be able to get that out of there. With high pressures and hydraulic fracturing fluid, they're injecting number 4 there, the propants, the small ceramic or silica sand to keep the fractures open. Then once the fractures are open, that water that's injected, about 30 to 40% comes back up to the surface. That's called flowback water. 30 to or 70% may be lost of the hydraulic fracturing fluid. Then once that occurs, then you have a producing well that's producing from the formation. So in this case, the Bakken formation. So a lot of us here in the room work on water quality issues, and I like to discuss that where there are humans, we potentially have effects on our water quality. And so agriculture, urban, naturally occurring heavy or trace metals. With respect to urban development, you know, we see PERC associated with dry cleaning. We have fertilizers on lawns that we see may affect water quality. Agriculture, pesticides, confined feeding lots. And then septic systems for private wells. You know, the idea that whatever's going down your drain potentially could get into our drinking water system. So you have all that as a potential water quality concerns. But you take that and you superimpose that on top of oil and gas development. Okay, areas of oil and gas development. This is a Ben Ghosh from Duke. He's produced a lot of papers, several in 2014. But this is a nice diagram that kind of shows all the individual pathways of concern in areas of oil and gas development. And I'd like to update this figure to be more relative of what the Williston Basin is, but this is a good cartoon for what you can see out there. So for number 1, so we have the water use. So water quality, but water use. So with respect to hydraulic fracturing, you know, I've seen numbers anywhere from 600,000 to 900,000 gallons of fresh water are used for the injection process. So this is our drinking water. This is our potable water. This is coming either from surface water sources or out there, the bedrock or glacial aquifers. Okay, so that's one element of concern, just water use. On the surface, you have, you know, all the transportation of the saline brines, of the petroleum product, of the for hydraulic fracturing fluids. So when you have that, you have potential for spills. The North Dakota Health Department reports 5 to 6 spills a day at the surface, and those are spills that are 5 gallons or more. So spills are occurring, that happens, just the sheer volume that we're talking about. Not so much now, but in the past there were unlined ponds where they would just dump the saline waters or the drill cuttings or the fluids. Processes are a lot more conformed now where they, you know, they don't do that anymore. So that's very protective. So in this case with wastewater treatment and storage ponds, it's not, hopefully not an issue in the Williston Basin. Although you have the artifact things, stuff that happened in the 50s that could still be showing up in today's drinking water. Let's talk about just conventional oil and gas wells that were started in the 50s up through still present day. With respect to the horizontal, the unconventional wells, you could have casing failures, you could have leaks. We're talking about very saline waters that are coming up under pressure initially, and over time, just fatigue, maybe not a good seal, but there's that potential for leakage or failure with time. Then we have the injection wells. So for all the saline water that's coming up out of the production zone, you have to deal with that saline water, and how it's dealt with in the Williston Basin primarily is re-injected back into the Dakota sandstone, lower Cretaceous. So in reality, for the Williston Basin, the injection wells are above where they are producing from the Bakken shales. Then on top of that, just increased population. On top of that, man camps and increased wastewater treatment issues and things like that. So a booming issue. Okay. So the study area that we're going to talk about today, the Williston Basin. It's a large structural basin in the U.S. and Canada. It's outlined in blue here. Montana and North Dakota. The wells here, obviously a data issue here, but these are all the wells, oil and gas development wells that are drilled in the basin or in the area. The extent of the Bakken Formation in red. So really the Williston Basin in like Mississippian age formations has been a large producer of oil and gas since the 1950s. But it hasn't been until the last 10 years or so that there's been a rapidly increasing development due to the unconventional oil and gas development from the Bakken and Three Forks formations. Okay. This is a plot of just the total number of wells, regardless of what formation they're producing from. So the bar charts here are just numbers of wells per year, okay? And then the red is the cumulative number of total wells in the area, okay? And that would be the right axis. There are about 10,000 producing wells right now in the Williston Basin. That includes both conventional and unconventional. As you can see, starting in the 40s, some peaks, the oil boom in the 80s. And then ultimately about 2000, we've seen it from the unconventional oil and gas development. Okay. And so this is just the Bakken Formation. And today I was working on this talk, and I have a problem with units and volumes, and when people talk millions of gallons and billions of gallons and barrels. But this hit home to me today was the idea that the daily production out of the Bakken Formation in the Williston Basin is now approaching 1 million barrels per day. Actually, the number I saw for right now is 1.1 million barrels per day. Now let's look at that with respect to a barrel is 42 gallons. And 1 million barrels a day would be 42 million gallons per day of petroleum, which is amazing. You take that 42,000 million gallons per day, that's 129 acre feet. Everybody has ways to visualize water, but to me, 129 acres, a foot deep, that's how much oil is produced per day in the Williston Basin from the Bakken Formation. Okay, that's pretty amazing. Okay, so there's 8,000 producing wells in the Bakken Formation now. They're predicting within the next 30 years, maybe up to 40 to 60,000 wells producing. So you multiply a 5-fold to 7.5 times what we see now. So again, as this oil comes up out of the ground, there's also saline water that comes up with it. Okay. So let's talk about the produced waters that come up with the oil. And so you see anything from, we sampled wells where it's entirely petroleum crude oil, not a single drop of water. It never separates. But for the most part, it's a gradation between maybe 1 to 5 parts. The average may be around three barrels of salt water for every barrel of oil. Okay, so let's look at simple math again. So if that would mean we have 3 million barrels of salt water produced a day out there in the Williston Basin. And so that's 126 million gallons a day, and that's 387 acre feet per day of salt water. So you add the soil or the salt water and the oil together, we're talking almost a section, a foot deep per day. So that puts it in perspective. And then all that salt water is being re-injected back into the ground and transported. Okay, so the Williston Basin, the Powder River and the Williston, and what we're talking about for bedrock aquifers are the Upper Fort Union, the Fox Hills, and the Hell Creek. There's also the glacial aquifers that are highly productive and actually the most productive in the area, but they only cover the north part of the Williston Basin. So to a depth of maybe 2,900 feet, these bedrock aquifers, potable water. And if you look at this for scale, if you were to go across the Williston Basin, the potable aquifers, the bedrock aquifers, would be a half an inch, and the basin would be 42 inches wide. So it's a really thin veneer relative to the overall spatial extent of the basin. Okay. So the potable aquifers, again, this is a cross-section from the southwest to the northeast across the Williston Basin. The glacial aquifers in the north, the continental glaciation. The tertiary aquifers, the Upper Fort Union, and then the Upper Cretaceous, Fox Hills, and Hell Creek. And then with respect to where they're injecting the water, the saline water back into the ground, it's the Dakota sandstone, Lower Cretaceous. And then the Bakken Formation is the area of energy production at this point, the big player. So what I wanted to point out here is maybe 2,000 feet of the upper bedrock aquifers, and then the Bakken's maybe 10,000 feet, so maybe 8,000 feet of vertical separation between the formations. Okay. So the produced waters, which I keep talking about. So produced waters is just basically the water that comes out of the production well, and it could be flowback water, it could be the injected water that goes into the well during the hydraulic fracturing process, and the formation waters that are in place within the formations. Combined, they're some of the most saline in the country. So within the Williston Basin, the red dots, we have TDS concentrations of 200,000 to over almost 450,000 parts per million TDS in these waters. Okay. And so why do we study water quality? It's kind of a simple question, I guess. And for me, you know, you see some documentaries like Fracking Hell and things like that where people are concerned that their water quality has changed since development or some other process has come in. And but there's really no documentation to show. And then they say, oh, it's sampled, and they say it's fine. Well, the idea is let's see what's there. Let's see what's there now and see if there's a trend in the future. So why do we sample the groundwater? It's our source of our drinking water. Okay. Current conditions, what's a snapshot in time? What are the current conditions of that drinking water? Do a full scale analysis, full suite of analysis on this water to know what's in there. And how does it change with time? Does it change with time? Produced waters, what's the concern? What's in that water that we should be worried about? You know, if it was leaking, let's say, at subsurface. And it can be used to differentiate between producing zones, between the Mississippian age versus the Devonian, the Bakken formation. And with respect to industry, it's a confirmation that their practices are working. If we find that there is no issues with respect to the produced waters and what's in our drinking water. And if there is, maybe some modification of industry procedures. And so for Bureau of Mines and for us and DNRC and DEQ, the idea is you collect this data and you make it publicly available. It's available to anybody, industry, public, water supply. You document the methods that you're sampling. People can come back 50 years from now and they know how you did it, what methods you used, the analytical processes. And you quality assure the data. You run blanks, replicates, your labs are quality assured, so your data is defensible. The idea is that you have it out there and everybody can trust it. Okay. So for our work in the last couple of years, it's been the produced water sampling, 25 wells in the Bakken and Three Forks formations, and basically to chemically characterize these waters, what's in them, and are they distinct from other formation waters. And then with respect to the water supply system, we focused on the Upper Fort Union. We randomly selected the wells. We're looking at current conditions, and really the take-home message for me is the age of the water. How old is that water you're sampling? Because you could be misled by grabbing a sample and not finding any constituents of concern in it maybe, and thinking everything's fine. So it's better to have the full suite. Okay, so for the produced water sampling, we sampled 25 production wells, 6 in Montana and 19 in North Dakota. We sampled them for major ions, your basic chemistry, trace elements, isotopes of strontium and oxygen, deuterium, and then radium isotopes. This is our first round of sampling in 2012. We sampled them, and we didn't know what to expect for temperature or how warm these waters would be when they come to the surface. And it was kind of an educational experience how to process them. This is Craig Bowers with one of the wells that absolutely, there was no produced water that came out of this. It was just solid petroleum product. Okay. So from that first round of sampling, we realized we're in a different ball game. The fact that, we're used to sampling domestic wells where you're looking at parts per billion, VOCs, and things like that. Here you're dealing with something that the degassing at the wellhead could maybe knock you over. So obviously safety procedures, and then the question I had when you sample these waters, so these are 2.5 gallon jugs directly from the wellhead, and you get this slurry that comes up when you sample. So it comes up almost as a froth, warm, and you grab your sample, and then it starts separating. And so the question is, what are we analyzing, and how comparable is it to someone else out there sampling? And did it matter how long that water sat before you processed it? the oxidation thing start to precipitate out. Should we be concerned about doing it within an hour, or can you go from wellhead to wellhead, grab all your samples, and then process them later? So for the first part of this study, this last round, we sampled at each wellhead. We grabbed 5 or 6 samples, and we processed them at 1 hour, 4 hours, and 24 hours. Did some replicates, and then we also sampled from the separators, because it'd be a lot easier and safer to just go out and sample from the separators where the oil and water is already separated and you're just sampling the brine. And the idea is to compare all that data to see how consistent it is and hopefully guide us in the future, or everybody in the future, that when you go out to these Bakken waters, it may not matter how fast you process after you sample. So, and then, with the rest of the wells, just a chemical characterization of what's in these waters, and do they vary throughout the basin, and compare it to other formations. There's one more thing I was going to say there. Okay, so just an example of the chemistry of the Bakken formation waters. So this is a typical well from the Bakken with total dissolved solid concentrations over 300,000, primarily sodium chloride, low sulfate. This is seawater, about 10 times more total dissolved solids than seawater. And this is just one of the Upper Fort Union wells that we sampled last year. So maybe 300 times the concentration of total dissolved solids in this Bakken water compared to our drinking water source. Okay, a graphic from Zell Peterman, just basically the same thing, just showing the order of magnitude difference between a Bakken well and seawater. So with respect to lithium, but let's say calcium, about the same. Chloride, about 10 times the concentration. So just another way to look at it. Okay. So far, not only the major ion chemistry, but stable isotopes of water, oxygen and deuterium, and also strontium isotopes look very distinct for the Bakken compared to other formation waters out there. So from the data set we have, it could be a fingerprint. If there is an issue arises in the future, or if there is a drinking water problem, maybe this chemical signature could tell you where the source water of the end member was from, in relation to maybe the historical drilling in the 50s through the 80s, which was conventional wells. Maybe that's the issue. So there is a differentiation between the water chemistry in these formations. At least that's what it looks like. Okay. So now we'll go to the drinking water side, the Upper Fort Union assessment. And this is primarily 34 wells, mostly about 14 in Montana and 20 in North Dakota. So our objective was to characterize the bedrock aquifers, what people are using in the system. Even though the glacial system has higher production, concentrating on the bedrock of the Upper Fort Union, Fox Hills, and Hell Creek, the Upper Fort Union was the biggest producer. So that's, for a start, that's where we started. So we focused on the Fort Union, which would be the can here in the cross section. So for the Upper Fort Union, we sampled 30 wells, but we also sampled 4 of the deeper Fox Hills, Hell Creek wells. And we analyzed them for a pretty extensive set of just major ions, trace elements, nutrients, a set of 23 VOCs, volatile organic compounds, methane and ethane, hydrogen and carbon isotopes of methane, and hydrogen gas composition. Okay. And then for 10 additional wells, or of those wells, we added an additional constituent list. The GRO, DRO, gas range organics, diesel range organics is kind of a screening. Dissolved organic carbon, hydrogen, oxygen, and strontium isotopes, which you can archive. So that's one thing you could do, is grab those samples when you're in the field, and you can process them later if something interesting comes out. Then we looked at age dating constituents, sulfur hexafluoride, tritium, and carbon-14. The noble gases or dissolved gases to help interpret recharge temperatures and interpretation of the age dating. This is a sampling for the dissolved gases, and the noble gases. So there's a few schools of thought, I guess, with regards to water quality assessments. You can go after a target. You can know that there's an issue. You can go by a well that could be the problem, so you put a network of wells around that, or you can go random. What's nice about a random distribution, it gives you a statistical feeling of what really people are drinking out there. You know, you're not biased towards maybe finding something, you're just doing a blanket. And how we've done it in the survey for several years is, you know, you pick your aquifer, and 30 is a good number if that's, you know, it's a good minimum for statistical purposes. And you just take that area and you divide it into 30 equal cells, okay? And within that, you pick all the wells you can find. In this case, you're finding wells that are completed in the Upper Fort Union Formation. Of that, we had about 1,000 wells, almost 1,100 wells to choose from. And from that, you just do a random pick of those wells within each one of those cells. So you pick your first choice and maybe up to 6 choices. And so the idea is you're not biased to finding a well for any reason other than it's random. That's how we typically do our studies when it comes to our distributions. So here's our network. The extent of the Upper Fort Union Formation, North Dakota, and Montana. The background here is the distribution of oil and gas wells, the 34 wells we sampled, and then the 10 wells that we did the extensive list of constituents. Okay. So being random, we didn't go after a well next to an oil and gas well. This is our distance to the nearest oil and gas well, the land surface location, not the lateral location, so it could be closer to these wells. But for the most part, we were about 4.5 kilometers to the nearest oil and gas well. And our closest well that we sampled was a 0.5 kilometer to the nearest oil and gas well. Okay, so the results from this study so far. From these wells, which were randomly selected, 0.5 kilometer or greater from any oil and gas well, we didn't find anything at all that had an indication that energy development had affected the water quality in these wells. So that's good news. Didn't find any, you know, highly saline waters or any kicks with the TDS that would have shown that. We found a few really small concentrations of VOCs that could be locally derived. A person replaced a pump or something like that. Methane. We did find methane in the wells, but the methane using the isotopic data shows that it was biogenic in origin, which means it was generated within that aquifer rather than thermogenic, which would have came from the Bakken Formation. So it looks like even though there's some elevated methane, it seems like it was generated in place through biological activity. And the lead author on this study was Pete McMahon, and it's supposed to be in Groundwater. It was supposed to be published last week, so we'll provide you with that. And that has all the data and interpretation of the age dating constituents and how we did the study. This money came from our headquarters, and so it's one of those deals, and I don't know if you fall into this category, but you have a substantial amount of money, but it has to be spent by the end of this year. So a group of us got together, and we threw a lot of things at it with respect to the analytical list. That maybe now in the future we could par down. The things that we analyzed here we may not do in the future. It was just, let's see what we get. And so the age dating, the methane isotopes are key ones, the major ions, of course, but like the DRO and GRO, maybe not in the future. So this talk said for laymen, but I'm looking around here, people are a lot of familiar faces, but I wanted to talk about groundwater age. So I said before that, you know, we didn't find anything that suggested that we had any issues out there with respect to water quality associated with energy development. But let's think about the flow paths. Let's think about the age of the water. Again, our nearest well, sampled well, was a half a kilometer from the nearest energy oil and gas well. So if we think about a flow path, we think about recharge to an aquifer at the surface, rain, snow melt. You know, as that water travels through the system, it becomes isolated from the atmosphere. And for age dating tools we use, for the younger age dating, 50 years or less, we use anthropogenic or human-caused constituents that are put up in the atmosphere, mix well in the atmosphere, hit the surface of the earth, or recharge the aquifer with our with our through the precipitation, but once it's isolated from the atmosphere, there's no more inputs from the atmosphere of these constituents. And tritium is one of them. Tritium, you know, the nuclear weapons testing in the 50s, we had a peak of tritium that has a half-life of 12.4 years. It's since dissipated, but if you look at tritium and helium-3, you can determine the original source concentration of that tritium. Sulfur hexafluoride, which is another constituent that they use in cover gas for transformers in the process. It's a greenhouse gas, mixes well in the atmosphere. It's still changing with time. It's another tracer. So with those constituents, you can look at, well, presence, absence, but you can also try to determine through modeling the actual age of that water along a flow path. And so in the Williston Basin, we concentrated mainly on the upper Fort Union. We'd analyze a few wells throughout from a recharge area towards the central part of the basin, just to look at the age of the groundwaters, and carbon-14 also for longer term. Oops. I'm glad this is recorded. Okay. So, most of the waters we sampled throughout the basin were predated energy development. So other than near the margins of the basin, near a recharge area, most of the water was recharged prior to 1950. So the water we sampled is older than the energy development out there. Okay, so that's an important point. We're not likely to find a constituent from that well because that water is older than those wells at this point in time. 20 years from now, 50 years from now, long term, that may show up with the network that we had. Looking at flow paths and where we did have constituents where we can measure the actual age of the water, they determined maybe 10 to 25 meters per year for the velocity of that water to flow. So this network, as we had it would not be very good at finding recent spills at the surface because that water's 50 years old or older at depth. Okay, and if you have a leaking well at depth, when you think about it, 2 miles of vertical, that you could have a failure at different depths. The idea that water travels at 20 or 10 to 25 meters per year, it's going to take a while to get to that well that's a half a kilometer away. Okay, so that's where I kind of think about the random distribution and also the targeted. So if, let's say, you put some monitoring wells near an oil and gas well, you still may be missing that vertical leakage because of your depth of your well. So there's a lot of complexity out there. Okay. So, you know, there's a lot of studies that are going out in the Williston Basin, and the USGS is just one of them. But the Bureau of Mines and Geology, I know they're with more recent energy development and questions. There's some studies that have occurred, Shields Valley, Carbon County, Stillwater County, some domestic wells, springs, and some streams. A lot of what's been analyzed is similar to what we've done with the survey. Some of that is in cooperation with DNRC, I guess, funding. But there's a list of projects that are going on besides the USGS. And I think through a DNRC grant, Bureau of Mines is increasing, or maybe in the future working on some more groundwater work with respect to the Williston Basin oil and gas development. I guess I have it here, but I can't read it in the dark. So, but the important thing is I hate to stand up here and say that we're the only ones doing this, that there are other agencies doing this, and this winter we're going to try to get together in Helena and talk about what everybody's doing so we can be on the same page, because it is an important issue, and build on what we're doing and what other agencies are doing to have a network that's meaningful and not overlapping. Okay. With respect to the USGS, we're working on, I'm just helping the Blackfeet tribe set up a monitoring network. It's kind of going slow, but the idea is just get a network set up in both the bedrock and the superficial aquifers so that they can go out and sample, and energy development there is kind of stagnated, but they can have some baseline data for the future, okay, and keep monitoring it. This last summer, through the National Water Quality Assessment Program, we sampled, I think, just 7 wells across northern Montana in the glacial aquifers. And that, again, is a lot of the same constituents that we measured as part of the Williston Basin study, so it's comparable. Joanna Thamke's been working in the Poplar area with respect to brine contamination, geophysical surveys, looking at migrating plumes, and she's been doing that since the 80s. They just flew a recent EM survey, I think this last month. In respect to water use in the basin, looking at just a consumptive use. So when we're talking about the water that's used for hydraulic fracturing, it's a little different than maybe a lot of the water rights and water use issues we have, because that water is injected back into the ground, never to be seen again for potable water. Versus irrigation, even domestic supplies where you go out to a drain field, you may be recharging your aquifer, right? This water is consumed. It's going down into another formation, never to be seen again. So the 900,000, 600,000 gallons for a hydraulic fracturing is water that's out of the game for, near future. So it's important to get some better numbers on those systems. Okay. And then one last overview of just about a year ago, working with the Energy Resources Program, there was a possibility there would be some money available through Congress to really hit this hard with respect to the money you need to do a full-scale assessment in the basin. And so we wrote some proposals. They may never go anywhere, but it's really what we all want to know. What are the current conditions in the Williston Basin with respect to the groundwater, the produced water, the flowback fluid, which is the hydraulic fracturing fluid that comes back to the well, and then surface water. Surface water is a great indicator of at least the recent spills, local flow paths, discharge from the system. So we had several phases of possibilities that maybe we could, if the money becomes available, we could hit it just like we did for the Upper Fort Union. Really just to initiate a comprehensive baseline monitoring network. Okay, and so the vision is something similar to the National Water Quality Assessment Program, not just the USGS, but where you have just a consistent data set, defensible, quality assured, consistent methods over a large region, where you can compare that data to the data that's collected elsewhere. And you can look at it through time. 20 years down the road, you have confidence in that data. I can't stress that enough. And so my take-home messages. The industry is very confident that what they're doing is a huge improvement to the 50s through the 80s with respect to disposal pits, unlined disposal pits. That doesn't occur anymore. Leaking casing with respect to the multiple casings and the cement seals around the actual injection wells and the production wells. So with those safeguards, that's a reassurance. But again, with respect to accidents still happen with respect to the surface spills of 5 to 6 a day, according to North Dakota Department of Health. That's what are reported. Subsurface leaks, the slow groundwater velocities, it may be a long time before it shows up. So it just stresses to me the importance of long-term monitoring. And long-term, maybe go back to the same wells every 5 years, maybe for a reduced constituent list or random, a greater density. Wells closer to oil and gas development, wells closer to injection wells at various depths would be important. And then surface water would be a key player to start looking at surface water as a combined integrator of what's going on near the surface. So, all right, thank you. Any questions? Yes.
So, in terms of sampling the produced water,
Mm-hmm.
is that a mixture of existing formation water and frac water?
Yes. That's great, because I'm glad you said that, because that was one of the things when I stopped there I wanted to say. So thank you very much. So the Energy Resources Program would really like to get a feel for that flowback water coming out. When we sampled, we made a point with industry to only sample wells that had been in production for over a year after they had been hydraulically fractured. So we try to make a point that water is kind of what you're going to see out of the bulk of these wells through time, okay? And also we found, learning experience, we found that they treat a lot of those wells. Actually, the one company, we had a list of 50 wells that we had candidates for. We had ended up with 5 because they treated continuous freshwater treatment of these Bakken wells to prevent scaling and salt buildup. So, you know, some of the earlier data where you see maybe people making interpretations that there's a shift along the isotopic line because it's a little lighter or heavier than the other waters. There's a possibility it's because that's injected fresh water into those wells and then they're sampling, you know, whatever's coming up. So for the data set, especially the 2014 August data set, we tried to make it pretty clear that these waters are from producing wells for a long period of time. Yeah. Mostly formation water. Yeah, that's your short answer. Yeah. Yeah. Thank you. Hi.
I can't visualize how you sample.
Yeah.
You know, like the domestic well, you know,
Right.
how do you physically
Yeah, let's see if there's a better picture, if I can. Okay. Yeah. Okay. So right at the wellhead here, so they usually have they had a pipe that had a pressure valve off to the side, and the producer would actually take out a plug, shut that off, take out a plug, and we found it's best to have a hose, a threaded hose that would fit. You know, we tried to get consistent with our setup. But basically, it's a purge right off the main line. That water's constant. The material is constantly coming up. We're just taking a diversion off the side. So we purge off the first couple gallons, and then we're just collecting raw material from that wellhead. So yeah, you have to collect everything. Yeah. What was nice is you leave it all with the industry, and they run it through their separator tanks. It kind of spurts out. It's a frothy mixture. It's everything, yeah. And so reportedly, when these wells are new, they're under a lot of pressure, higher temperatures, but we didn't have any of that issue with these. But yeah, it's strange. And then it's degassing. It stinks. And the first time we did this in 2012, you know, Williston Basin, the wind blows, you know. And so how we did it before, we had that salsa bottle, and we were decanting the oil off the top with the peristaltic pump. And then you would collect the brine water underneath, and, you know, but get lightheaded, poor ventilation. So, you know, the safety guys came out this time, but ideally you want to do it outside if you can, at the very least, under a hood if you can. Proper ventilation's huge. But now we use these, and I think this is the way we're going to do it in the future, is those carboys, which is basically how the Energy Resources Program has done it in the past, and LECO and others, a similar fashion. But you take a carboy, and I wouldn't do a collapsible one. I would use a hard-sided carboy, and basically you invert it so the oil's on top, and you pull the sample off the bottom. Okay. So again, there's going to be this function when we get the data back. What does it matter? What does it matter about processing time? I still have a concern about things precipitating out. And the analyst for so far said he hasn't seen hardly any difference in this data between processing at 1 hour, processing at 24 hours. But I still have a question regarding a filtered sample and a raw sample. You got to realize there's not too many labs that can handle this water, too. It's not an easy find to find laboratories that will analyze these waters that are 10,000 times saltier than the ocean, and they have to do a lot of dilution. So there's some concern about maybe it doesn't matter, maybe it's nasty water and it's within these error bars, but it's still a question to me is filtered versus dissolved phase or whole water. We found too, I'll just share if I can, you know, find it better if you have like an elbow injecting it into the water bottle and be away from it so you're not standing right over the water bottle as you're sampling it because it's degassing. When you're processing the samples, by the end of the day, everything's coated with salt, you know, a nice veneer over everything. Work with the industry to know where to dispose of everything when you're done, because you don't want these empty bottles and rags, but they're pretty good about it if you make arrangements that they'll take everything off and dispose of it properly. So, yeah, thanks.
When you inject water into the sandstone, what do you displace? You understand what I'm asking?
It's under,
That's displaced or a gas or a liquid or what?
well, it's under higher pressures. It's higher pressures, and then you get that pressure back. So it's injecting under higher pressures with the perforated. So under the long 2-mile pipe, and someone could help me because I'm reaching here, but 2-mile pipe, you're fracturing it, perforating it like, yeah.
I'm thinking
Oh.
injection well, not
Oh, yeah, you're increasing the pressure, and supposedly I don't think this Dakota crops out, but you're pressurizing that.
pouring water some other place, or you're
Oh, yeah.
increasing the gas some other place, or what?
Yeah, you're increasing the pressure. You're going to get movement from those injection wells. Mm-hmm.
What's in the rock now? Rock
Water. Yes, water. Thank you. Yeah, it's an aquifer basically, but a highly more saline water. Yeah. Mm-hmm. Yeah. Thank you. Yeah. That's a question I have. And the idea it's so deep, it's not a concern, but
Before they can permit one of those, they have to prove that that water is good if it's positive PDS.
okay, so it's not drinkable at this point. Yeah. Yeah.
So they also, when it was there, has to be something.
Yeah. Mm-hmm.
It took 5 to 7 hours.
Mm-hmm. Thanks, Tom. So this is the Dakota sandstone. Yeah, to hit the glacial aquifer. I know. I've had the same. There's a lot to do out there, and I've had the same thought. With time, it's overpressurizing. It's going to change. You know. Yep. Yeah. That's a good question. I would hope so. Yeah. Yeah.
You said you would consider any other additives to the fracking fluid, like biocides, or I've seen other studies where biocides
Yep.
are evaluated.
Mhm.
Is there anything you're doing?
No. And I'll say too that this is one little study, 30-some wells, and then and we tried to stay away from the hydraulic fracturing material fluid, but it's hugely important to me. That's what you hear about. You don't hear about, to me, the brines. To me that's the long-term legacy issue, is the brines. The fracking fluid is something that goes in the ground. A lot of it comes back up, but quantifying it, the brines are a lot larger volume that's going to keep going for years. But so for the proposed study is to more look at the actual fracking fluid, how much recovery, how long does it take to come back out of the formation. But for this, it was just kind of two end members. What are we drinking now? And the formation water. There's all these players in between that are still, at least for me, haven't been studied. So, yeah, but it's a good question. Yeah.
Is the high salinity of the produced water, is that the fluid that's being used for fracking?
You know, initially, it was just fresh water. Now they're trying to work with processes where they can use the more saline water in the fracturing process, which would be logical. Yes. Mm-hmm. Good question. Yeah.
So you, on all the wells that you sampled before you were looking for contaminants, and you didn't find any thermogenic gas or oil, did you find anything like from agricultural or residential?
Yeah. Yeah.
Nitrates or other things that might be
Right. We did find one arsenic that was above the drinking water standard, naturally occurring. Nitrate, I think we had a couple near, I actually have the data, but like 5, didn't exceed. We did have a couple hits of VOCs, but they seemed localized. It didn't seem like something coming from 10 miles away. From the overall health for each well we sample, we provide the data to the owner and give them a description. There was fluoride was elevated, but there was, and we didn't sample for pesticides. So
nothing to suggest year-round septic system.
no.
It's pretty good water.
Well, for that area, yeah. For us, it wouldn't be that great. You know, TDS of 1,500, yeah. Yeah. So, yeah, John. Yeah. Yeah, that's true. Can't chew it. Yeah, yeah. But it's the only water they have. So. Mhm. Yeah. Mhm. Yeah, is it dampened or higher? Yeah. Yeah. I wish I did. There's a lot I have to learn. That's a good one, John. So, yeah. Yes, sir.
How much tritium did you find and what was its source?
Atmospheric.
Tritium costs both proteins and nutrients.
It was.
It's already a topic.
There's, for the most part, because of its decay. Um, correct me if I'm wrong, but right now I think it's very low concentrations of tritium are coming down in the precip. Okay, you can have tritium from other sources, and through Pete's work, he was able to decipher through helium-3 and tritium that the end member of where that tritium came from, the original concentration of that. From helium-3, he was able to back calculate the original concentration of tritium, and they're able to look at these other noble gases. I guess this isn't something I'm an expert on, as you could tell, but figure out different sources of that tritium, which could be, I guess there's other sources in nature, but not at these concentrations. So. Yes.
Are there parallel studies like this going on in Saskatchewan and the southern border?
I've seen some produced water studies coming out of the northern side of the border just recently. So, with respect to just overall drinking water, I'm not sure, but I have seen some recent produced water data that's going to be very comparable to what's been collected out there on this side. So, yeah. Yes. So, the Energy Resources Research Program, Brian Engel. Yeah, so that and the Piance Basin in Colorado, yeah, in Texas. There's other studies that are similar. So, yeah. Hard questions. Thank you. And there's several reports up here if anybody's interested. Some handouts and a recent fact sheet that talks about the Bakken